Okay guys, so today we're going to be talking about arc length. Arc length is the length of an arc of a curve, and it can also represent the distance an object travels. Essentially, if we have a curvy function instead of a straight line, we don't know how to tell how long that curvy piece is, but our arc length formula is going to be able to tell us how long that curvy piece is. Our formula comes from our distance formula. Our distance is formula from, pre-algebra or algebra 1. It essentially is our Pythagorean theorem. Okay, that the distance is the difference of the x's squared plus the difference of the y squared all inside a square root. And what we're going to do to use that formula to figure out distance, we need to make linear segments on our graph. So if, let's say, this is my function, and I want to know the distance on the graph from point A to point B, okay, what I would start by doing would be taking the distance between these 2 points to approximate the actual length of the curve. Now, if I find the length of that red line, let's pretend that it actually connects those 2 points. But if I find the length of that red line, it'll be an estimation of the actual length along the curve, which would be this length over, this length over here. Okay, so it's that red segment is an approximation to the actual arc length that I'm looking at. It's not a great approximation, but it's a decent approximation. Okay, and I would find the length using this lovely little distance formula here. Okay, to better our approximation, instead of just connecting the endpoints and finding the distance to the endpoints, I can make another segment. Let's say I cut the interval halfway and start connecting points at that midway mark and find the length of those 2 blue lines. Okay, now the length of the 2 blue lines, if I collect them together, will be better to approximate the length of the red than the length of the red line was. Okay, and then if I want to get a better approximation, I would just use more line segments. So if I connect here and find that length, and that length, okay, I would get a better approximation, and I can keep doing this and doing more and more line segments, okay, and I would always find the length of each line segment by using our lovely little distance formula. All right, so I'm going to go through this in a very broad and crude way. If I want to find the length of each of these little line segments, okay, and I did new line segments, but if I want to find the length of each one, I'm going to do my little distance formula. Now, I'm going to be breaking up the length of my whole interval into a certain number of segments. Let's say I divide it into n segments. Okay, and if I'm dividing it into n segments, this should sound like area and volume, then the length of that interval would be, each little subinterval would be b minus a over n. Okay, and if you remember, we were calling that a delta x. Okay, so the length of each little interval is delta x, but that's also the difference between my x values. So my distance would be a delta x squared plus, and then the difference between my y's would be equivalent to a delta y value. Okay? Okay, so what I want to take from that is that our distance formula is essentially the same as having the difference of our x's, or delta x quantity squared, plus the difference of our y's, or delta y quantity squared, and the sum of those and the square root of that. That's our distance formula that comes from Pythagorean theorem. What we're going to be doing is we're going to be adding up a bunch of these tiny little distances, and that would give us a Riemann sum of them. Okay. I apologize because this is my first video with a new program, so I'm learning the ropes. So I would have a Riemann sum of a bunch of these distances by finding between endpoints. And it would be a delta x sub I squared and a delta y sub I squared. Okay, so I would sum them up, all right? And then in order to go from a crude approximation to a great value, a true value to my actual length, I would take a limit as I had more and more and more of these little tiny segments. So a limit of a sum. Okay, my delta x squared plus my delta y squared. Okay, now, again, like I said, this is a very crude adaptation, but what this ends up being in terms of calculus, a limit of a sum would become an integral, okay, from one endpoint to the other, and the square root of, now I would have a delta x, and delta x's is something that we used in Algebra 1 and Algebra 2, and we saw how our delta x earlier in AB became a differential, a dx. Okay, so I'm going to convert my delta x's to dx's and my delta y's to dy's. Okay, so this is what I'm working with. Now, this integral isn't complete because it doesn't have a differential at the end, and we solve that by manipulating this a little bit. Okay. Okay, so working with this formula, the way that I'm going to manipulate this is I'm going to divide out or factor out if I have y as a function of x. Okay, so if y is a function of x, I'm going to factor out a dx quantity squared. Okay, so what that would look like is I'd have the integral of, and I'm going to factor out a dx quantity squared. And if I factor out, I'll have a times a 1 plus. And if I'm factoring out of a dx quantity squared, I don't have a dx quantity squared, so I'd have to have a dy quantity squared over a dx quantity squared. Okay, and then what that allows me to do is I can divorce my square root, and I can have the square root of dx squared times the square root of 1 plus, and that's a dy squared over a dx squared. I'm just going to make it a dy dx quantity squared. Okay, and then what happens here is that the square root of dx squared just becomes a dx, so I end up with the integral of 1 plus, or dy dx squared, and then the square root of dx squared is just a dx, and that becomes my differential at the end, which is what I needed. Okay, and now this is my arc length formula. Okay, so this is the formula that I'm going to take with me and I'm going to memorize. Okay, let me show you what it would look like if we had a function in terms of y instead of in terms of x. Okay, so I'm going to start with that same integral of the square root of dx squared plus dy squared with my differentials. And now if I have x as a function of y, that means that my derivative would have a dx dy in it. Okay, and in order to solve that, to make that integral functional with x as a function of y, I'm going to do the same process that I did last time, but I'm going to factor out a dy quantity squared. So go ahead and pause the video, factor out your dy quantity squared, and see if you can get down to a nice little integral that has a dy differential at the end. When you're done, you can come back to me. So initially, if I just factor out my dy squared, I have dy, inside the integral, inside the square root, I have a dy squared times the quantity dx over dy quantity squared plus 1. Okay, we're going to split up the integral. I misspoke, split up the square root, and we get like this, and then we're going to simplify the square root of dy squared, and we end up with our final integral. And this is what it looks like. Okay. Okay, so just to recap, our arc length formulas, whatever our function is, and it doesn't matter if we have y as a function of x or x as a function of y. Either way, we're going to take the derivative of our function. Okay, the derivative of our function. We're going to square it. We're going to add 1 to it. We're going to throw it underneath that square root, and we're going to throw it inside an integral. Okay, just make sure that if you're integrating with respect to x, that the bounds would be according to your x-axis, and if you're integrating with respect to y, then your bounds would be according to the y-axis. Okay, these formulas are very plug and chug. There's nothing fancy to do with them. You just have to take your derivative, square it, add 1, inside a square root, inside an integral, and you got to memorize the formula. It helps to know where the formula came from, so make sure that you feel comfortable with where the formula comes from. It'll help you understand or remember what the formula is in the future. Just note that these integrals are complicated and they're composites, and 99% of the time they are not integrable by hand. Okay, you need to just throw them into a calculator if you want to get a numerical answer for them. All right, we're going to do one quick example, and then you guys should just be able to plug and chug using the formula. Okay, so we're not going to do one that says find the arc length of, because then you know that you have to use your arc length formula, and you just, again, take your derivative, square it, add 1, inside square root, inside integral. Okay, here's one that says if an object travels along the curve y equals e to the x, find the distance from x equals 1 to x equals 4. Okay, so the process is really very, very easy. Okay, I'm going to start by taking my derivative, and the derivative of e to the x is e to the x. Okay, to find my arc length, I'm going to do my derivative. I'm going to square it. Okay, I'm going to add 1 to that. I'm going to throw that inside a square root, and I'm going to integrate it. This one's with respect to x, and from 1 to 4. Okay, if I want a value to this, I have to put it into a calculator because this is a composite function, and it's not integrable by hand. Okay, if you want to simplify it, you can, but honestly, just set it up. So I'm not going to even bother. I will throw it into my calculator and get a number, and that number is 52.052. Okay, so it's an easy concept. It's an easy formula. You just have to memorize it.